this type of the question is not that easy. One of the reasons is that both microbiome and omics data are high dimensional. So by high dimensional, I mean in this formula, K is larger than N, and M is also larger than N. This will make the number of parameters as M times K that we need to estimate, which is the dimension of the B matrix. And that is also way larger than the sample size, which could be a barrier. And that's the reason we thought about the regularization-based methods, which is well known in machine learning, and the core functioning of it is reduce the number of predictors that we need to, a number of the estimators that we need to estimate. But those framework doesn't really work on microbiome data integration. Why is that? Because there is an actual layer called compositionality of microbiome data. And in order to understand what is the compositionality of microbiome data, let's talk about what is the definition of absolute abundance and relative abundance. And for absolute abundance, everyone could imagine it's basically the actual amount of microbes that belongs to each taxon. But for the relative abundance, it is actually a proportion of the microbes in a sample that belongs to each taxon. And then in real life, the absolute abundance is not always observed. Actually, it's actually really hard to observe. So one question, natural question that we come up with is, okay, how these two data types differs with each other. And here is a toy example that I come up with. So the upper one is absolute abundance data and the low one is relative abundance data. And let's assume that we only have three subjects, and each subject we only have 3 taxons. And it's basically a count type of data for each taxons. And note that at the last column, there is a thing called total abundance, which is the summation across a summation of all taxons across one samples. So for the first subjects, 50 is equal to 20 plus 10 plus 20. On the other hand, for the relative abundance, the type of data has a percentage or decimal kind of structures, and how it calculated, for example, for the first subjects in the first taxon is 20 divided by 50, and that is the relative proportion. And then at this point, people would argue like, okay, so you still need the total abundance to calculate the relative abundance, which is incorrect because that is actually involved the sequencing kind of technology there. The quote-unquote fake total abundance that we get from the sequencing is called sequencing depth, and that does not have any influence with the total abundance. So it does not carry any biological information, but we still could get a relative abundance data. So in summary, the difference between these two data is first, the absolute data contains actual biological information, which is total abundance data. And for the RA data, relative abundance data, we have an actual constraint that all the RA cross all taxon from one subject sums up to 1. So how can we deal with that? Because A data is really available. So there is recent research trying to find a technique that can actually measure the absolute abundance data, but there are actual limitations for those methods, and though none of them, based on my review, none of them is well adopted to real worlds because the actual limitations, and some of them are very costly and some of them are not that stable. So another approach that people are trying to do is like, okay, let's handle this compositionality features of microbiome and then just use the RA data and combine with the paired omics data and trying to draw the conclusions based on RA-based association. And then, naturally, we want to ask, okay, so why your research makes sense or matters? the important question here is, what's wrong with using RA association? So go back to our toy example and let's focus on the taxon 1 and compare it to this 2 data type. To better understand, I have a visualization here. So from the left-handed of subplots, we can see that as the metabolites increase, the microbiome also increase. So naturally we would say, okay, there is a positive association between these two. However, if we use the relative abundance data, as we can see, the direction is totally changed, and that leads to the first type of misleading result, which is the incorrect direction. And let's focus on the taxon 3 for this example, and it is very easy to see that the taxon 3's abundance is the same across all the subjects in absolute abundance, but it's different in RA. To better visualize this, as we can see, as metabolites goes up, if we use the absolute abundance, then the microbiome taxon counts does not change at all. So we would interpret this as there is no association between these two. However, again, if we use RA data, it's a strong negative association there. So this is the second type of misleading results, and we summarize as the spurious association. To summarize, the challenge we're facing is that absolute abundance are very costly to measure, or it's not stable, and that most existing microbiome data already existed are all measured in RA data. So we wanted to come up with something. And then the formal PhD students, Dr. Hu, proposed the methods that use RA data to estimate the effects of microbiome AAs on omics response. But in some circumstances, it is interesting to see what the omics effects on microbiome AA as well. So in this dissertation on this defense, we're trying to come up with methods to estimate the omics effects on microbiome AAs, and hopefully only require RA data. So the first project we did is a penalized regression for absolute abundance-based microbiome multi-omics associations, and we call this model as PREMA. And for this presentation, we're gonna mostly focus on the second project, and then, but let's still touch base on it. So for the model setup of my first project, let's assume that we observe AA first. And what we want to do is we wanted to model log transformation of AA to some regression model, linear regression model. But it's just because we only observe RA, and we are trying to build the connections, use the log transform of RA to the linear regression model. So luckily, we do find the connections. And let's assume that W is AA and V is RA. As I mentioned before, RA is calculated by AA divided by the total abundance. So after we use the log transformation there, then the beauty of it is eventually we can see the log of RA is equal to log of AA and minus a log of total abundance. So eventually we will have the formula at the bottom that on the right-hand side we do have RA, on the left-hand side we do have our regular terms of linear regression, but we have an extra term of TI, which is trying to handle the total abundance. And as we mentioned before, the regularization kind of methods is involved in all 2 projects, and for this project we specifically pick the reduced rank penalty. And there is 2 type of kind of rank penalty there for us to choose. The first one is penalized on the single value of B, which is called a nuclear norm. The pros of it is it's directly penalized on the rank of B's, but it is actually very computational intensive because they don't have an explicit form for it. So to compromise that, we choose to use the adaptive nucleon norm, even though it's sort of penalized on the singular value of the xb, but it still could infer that B is sort of have a low rank structures, but it does solve the computational intensive there. And another reason that we are choosing the reduced rank penalty is we're trying to capture the functional redundancy of microbiome. So in short, it's basically, you can imagine that if we change some abundance of microbiome, a set of microbiome, to maintain the same associations, you can carefully adjust another set of microbiome, increase or decrease. So to understand better of what we are actually penalized, this is the picture that I came up with. So first we have two data sets. We have one microbiome data there, and we have another omics data in the bottom. And in this picture, let's say metabolism data as an example. So instead of drawing direct connections between each microbiome and each metabolites, we assume that there is a middle layer in there, and we are trying to find the linear components of microbiome, and here let's call it microbiome score, and then the linear components of metabolism, and then let's call it metabolism score, and pair them together, and each pair is a channel. And we believe these are the main channels that these two data types interact with each other. And by penalize on rank, we're actually giving the assumptions that the number of this type of channel is limited. So in this case, we only have 3 important channels in this graphs. And here is the matrix form of whatever I just basically said, and I want to emphasize that B matrix, association matrix, is the parameter that we want to estimate. And now, it is an AA-based association matrix now. And the object functions that we have is as following. As I mentioned, that the penalized term that we use is the adaptive nucleon norm, and we successfully proved that this object functions is a convex functions, which is great. And we also come up with the iterative algorithm and also proved that that algorithm converged to a global optimum as well for that project. And we use this type of model to the human microbiome project, phase 2. And it's basically the inflammatory bone disease data. And the microbiome data was based on whole genome sequencing. And after some data cleaning, we end up with 122 taxons under the species level, and then 177 metabolites. We only have 102 subjects in total, and it is across 3 diagnosis groups. 1 of them are healthy people, and 2 of them are diagnosed as IBD, but it's different type of IBDs. And in order to capture the baseline of diagnosis, we encrypt that diagnosis as an actual linear covariance in the model. So whatever we get from the B, we want to focus on the common channels of how microbiome and metabolites interact regardless of the diagnosis. And while we're doing analysis, we also ask ourselves that if the microbiome scores or metabolite scores behaves different across the diagnosis. So here is one set of the results that we get. We get the estimation of B's, which is a matrix, and of course we can look at each entry of B's and find the strongest association pairs. And here is the top 5 strongest things, and we have the raw coefficients there, and the parenthesis after log transformation. And I won't read through it, but I just want to point out, because we did the log transformation, so the impact that we are trying to do will be multipliable instead of additive. And as I said, another question that we are trying to answer is, how do they differ? Are they differ in microbiome score or metabolite score, and how do they differ? So in this real data analysis, we find 8 main channels, and like PCA, 3 most important channels explain above 90% of variations of the data. So we just dive in deep and look at the top 3 channels. And this is the 3rd most important channels, and we see the difference there. If we look at the box plots between non-IBD and UC for both metabolites and a microbiome score, we can kind of have the hypothesis that they are kind of different. So we did do the t-test there, and we do find a significant p-values there. So in the future study, we do have the components of these 2 scores, and we have loadings for these 2 scores. And we could look in details of what metabolites or what microbes actually make this change. So that's about my first project. And inspired by the first project, we did another project based on the group regression, and we call this model as GRAMMA. So as I said, from the previous analysis, we can see that there is different type of diagnosis. And we are interested in comparing the associations or networks between different groups. And then also from a lot of literature review, there are some of experimental design involved in this type of study as well. So a lot of them actually have a control group and have a treatment group, and they are trying to see what is the difference between them. And again, by comparing these 2 things, of course we want to see what is the common interactions, for sure. But most importantly, we want to see what is the differential interactions. And the difference is not actually that easy, because they can differ in different type of ways. So for example, there will be some interactions or associations unique to one group, but not the others. That's one type of differential, right? And then another type of differential would be it is positive associated for one group and negative another one. Or you can flip this. And there could be strength differs. Like they have the same directions, but the strength of the association is different from groups. So to do that, we come up with this model that focus on 2 groups. Focus on trying to find the difference between 2 groups. And I want to emphasize that for the left-handed of the equation, we have the RA data there, and we do have a T term as the previous project did. And what is new here is the 2nd term and 4th term there, and both terms involved UI, which is sort of a indicator for 2 groups. And because we are focusing 2 groups, and let's just say we encode it as 0 and 1s. And here, let's start to staring at this equation for a little bit. Assuming that UI is 0, then the 2nd term and 4th term are gonna vanish, right? And then so the beta 0k is trying to capture the baseline in microbiome in microbiomes for whatever the group encoded as 0. But if we change UI to 1, then we can see the first 2 terms can combine together, and 3rd term and 4th term can also combine together. And for whatever the group encoded as 1, the baseline is captured by beta 0k plus gamma 0k. And similarly, the association between groups, associations in the groups encoded as 1 is BJK plus CJK. And then that is the reason that we emphasize the beta 0k is actually trying to capture the difference baseline, the baseline difference in microbiome between groups. And then CJK is trying to capture the difference between groups in the effect of predictor J to taxon K. And here is the matrix form that we come up with. And hypothetically, let's just say B1 is the control group, and B3 is equal to B1 plus B2. It's just like the Bij plus Cij from previous slides is the treatment group, or whatever the other group besides of the control group. And B2 here is actually captured the differential association matrix. And those three matrix is the main parameters that we want to estimate. And the penalty that we are choosing here is the L1 penalty, which is a well-known sparse kind of induced penalties. And it could pinpoint the specific variables whose association are either common or differential between groups. So commonly, we come up with the following object functions with assumptions that the control group has a sparse pattern, and the differential association also has a sparse pattern. However, this type of object functions has a pitfall, which is sensitive to arbitrary encoding. So if we say the control group is encoded as 0, then we are actually penalized on the control group and the differential association. However, if we encoded treatment group as 0, then the model is actually penalized on the treatment group and the difference associations. And of course, they're going to give us different type of results. So in summary, the penalty is sensitive to the encoding methods. Maybe for the control and treatment, we can set up a uniform line, but there will be the cases as diagnosis, which group that you want encoded as 0 is seriously arbitrary. So the solutions we come up with is adding an actual penalty on B1 plus B2. And we call this penalty as the invariant penalty. And now the penalty structures between groups is actually symmetric. And we successfully proved that the object function is convex, and we apply the coordinate descent algorithm to get the estimations. And in order to update B1 and B2, we derive this double soft stretch procedure. And people who know Lasso knows the soft threshold estimators. And this procedure is exactly inspired by that. But the difference here is that in order to update B1, the corresponding entry is actually depend on the same position of B2. And if that is 0, if B2 is 0, then it is just the soft threshold estimate, because that's a lasso. But if it is not, then things get more complicated. But the calculation procedures is very similar to the soft threshold we come up with. And here for the B1 hat, it is the ordinary least square estimator, and for the T, it's the threshold that we need to calculate as well. And for tuning the parameters lambda here, we choose to use the generalized cross validations, and it has been proved that it's very useful, especially in high dimensional variation kind of regressions. Okay, let's jump in the simulation studies that I did. First of all, I have 4 different dimension settings. Besides of the low dimension, which is the n is larger than m, all other 3 settings, n is smaller than m, meaning that the number of predictors is actually larger than the sample size. And we have 2 signal strengths. Basically, it's just the different amount of errors that we put in the model. We have 2 variation of t's. Based on different dimensions, we have slightly different settings. And eventually, we generalize beta, gamma, B1, B2, use some normal distributions. And in general, it's just like the larger dimensions, we want to put a little bit more signal strengths there. And in total, there is 16 different combinations that we went through, and for each combinations, we have 50 replicates. And another very interesting part of doing this project or these simulations is to generate Bs. Even though I just said like, oh, both our assumptions is as simple as like, oh, these matrix is sparse, but it's actually not that straightforward to generate Bs. Why is that? Because they differ in different ways, and we want to have that feature embedded while we are generated Bs. And here is a lot of text. Feel free to read it. But here is the visualizations help us to better understand it. So for B1, we want to make it sparse. Then that's simple. 90% of the entries is 0. 10% of them are not 0. Easy. And then we want to generate a B3, which is another group. Then things becomes complicated. So my generation step is first, in this non-zero set entries of B1, those entries, 30% of those entries is 0. What does that mean? That means for B1, for control group, the association presents. And for the treatment group, those association does not present. So that is basically saying the association only appears in one group. And then for this dark green term, that is means both the association appears both in control group and treatment group, but they have different magnitude or the direction might change. And lastly, we have the other 40% of them saying that, okay, they are both presents and the association presents in both groups and they are equal. So that's actually a commonality thing. And in order to make sure that B1 and B3 have same sparsity, after careful calculating, you can do this 3% of saying B1 is 0 and B3 is not equal to 0. After this generalizations, what we are making sure is that B1 and B3 have the same sparsity, which is 90%. And better, the B2, which is the differential association matrix, having 91% of sparse, which is roughly similar to the B1 and B3. And we have our model here, and then we want to try to compare 4 other models. Here is a table that illustrates that we care about 4 components: the total abundance T, and then the penalizations on B1, B2, and B3. So for the base method, it does not incorporate T, and it doesn't care about the penalized on the treatment associations. And then without T, it's just have all the penalizations that we want, but we don't have the T term there. Similar as like W without diff and without B3, it's just losing one penalty term there. And to evaluate the performance, we calculate the estimation accuracy, which is called average mean square error for basically B's, all B's, B1, B2, B3, and T, and we calculate the correlations of T, and lastly, we do check the sparsity patterns using RC curve. And here is a table, please don't read the number. What I want to emphasize here is this column is our model, and I shadowed it because they have the best performance across all the methods. And as we can see, there is little things here and there, but if you look close, the difference is not that large. And also by looking at how much area that I shadowed, we can say that our methods actually outperforms in most of times. And here is a better visualizations for that. For one settings, which is high dimensional, high variance of T, and low signal strengths. And this pinkish or orange, this color, is our methods. And as we can see, the mean square error is at the bottom. And not surprised, our base model performance is at the top. Then we do check about the RC curve. And we have 5 different methods, and then that is the settings at the top. And one thing that I want to emphasize is this, again, this reddish RC curve is our methods. And if we look across all 3 kind of B's, we still could claim that our methods did a great job. And then the next slides, the only thing I changed from last slides is this variance of t, from low to high now. Interestingly, for the methods that incorporate t, their performance is very similar with before. But for the methods does not incorporate with t, then their performance is highly decreased. So in conclusions, including t definitely improves the estimation accuracy and sparse precisions, and especially when the variance in t is actually high. And then we penalized on B2, which promotes the commonality between groups, and then that helps us on detecting the differential interactions. And then our model outperforms all other methods on the sparse detection. And we applied this data to zebrafish data, which has come from Tom Sharpton's lab. And here is the experiment design. So on day 1, we have 100 fish swim there, and half of them are introduced to antibiotics. And then on day 3, they basically change the tank of water and get measured of the microbiome data and the metabolites data. And half of the fish that have antibiotics are exposed to the parasites. And also half of the fish that does not have antibiotics exposed to parasites. So on day 32, we have 4 groups of fish, and the microbiome data and metabolite data is also measured there. But for this data analysis, we're trying to investigate the microbiome antibiotic effects on the association between zebrafish microbiome and the metabolomes. So here we use the day 3 data only. After some data cleaning stuff, we have 89 general left there and 299 positive metabolites for our predictors. There is in total 83 observations that have microbiome and the metabolites, because some fish, I think, die eventually on day 3, and 37 of them is in treatment group, and 46 are in control group. And for the treatment group, I mean the antibiotics introduced group. And here are some results that we had. First of all, we want to compare 2 networks, and we want to see what is fun. And as we can see, that most of the associations are zeros in both groups, which makes sense actually in reality. And then there is a very interesting part at the bottom, which is the sign change, meaning that the association is positive in one group and negative in another. And there is only 27 of them in total, and that is only 0.1% of the entries. And then there are still like interesting things, as some association only appears in one group. So let's dive in deep on the most interesting stuff, and here is the table of top 5 association with sign changes. So meaning that one of the group has negative and another one have the positive, or vice versa. And we find out that this pair have the most significant difference. And it is well known that antibiotics is gonna significantly alter the composition or balance for microbiome. And this third thing is ceramide. I think one type of ceramide that is commonly found in some sort of lipids. So the hypothesis that we could give here is that the antibiotics may impact on the microbiome's abundance, and then eventually interferes or affects the lipid metabolism. And another interesting thing that we find is this table that shows here is the association only appears in antibiotics groups. And then we find that this fourth largest coefficients there. And then for the microbiome part, this pseudomonas is actually well known as an antibiotics resistance mechanism. So basically, in my interpretation, if you take antibiotics, that abundance is actually gonna go up. And then we have this sphingosine that have some sort of form, but anyways, the things related to that plays a crucial role in the immune system. So of course, I think everyone would have the common sense that the antibiotics may compromise the immune system. But here is a more detailed interpretation of how they impact the metabolism and then they eventually cause the immune system weaker. Another set of the results that we can come up with is compare the dominant association between groups. And then the first, because they're super hard to pronounce, so anyways, the first two pairs appears in both control groups and treatment groups, meaning that introduced antibiotics doesn't impact the association between them. But the third pairs here is the pairs only existed in the control group. And the fourth pairs is the pairs only existed in the treatment group. That means antibiotics definitely did something for the association there. And then there is definitely more pairs. I'm just putting the most severe one there. So for the conclusion of this defense, we first highlight the pitfall of just using the RA associations to approximate the AA-based associations, and we come up with two models that are trying to deal with that problem, use their IA data. And for the first project, we're trying to introduce the rank-deficient structures to capture the functional redundancy for the microbiome. And for the second project, we are trying to use the L1 penalty to see the two groups' association difference. And then we analyzed IHP data and zebrafish data to illustrate our methods. And future work is also very important and also very fun to look at. First of all, for my second project, the double stretch hooding, soft hooding procedure is actually very time consuming, as you can see, because it's mapping each entries to another matrix, but the dimension of the entries, the dimension of matrix is so large. So one thing we could do is trying to apply this ADMM algorithm, and it would simplify one steps to just pure lasso, which already have a package existed to do that. And that is one thing that we could definitely try. And another thing for the second project is that this approach could be extended to more than two groups, and the logic could be the same. And even better, in that group, we can eventually maybe deal with some ordinal categories and trying to compare the either time difference and then time changing point stuff. Okay, last I wanted to thank Duo as my advisor. She's such an amazing advisor. I have so many questions, not only on the academia, but also on the daily life, and she's trying to help me handling those things, and especially when I'm going through a really hard time for my personal life, she gave me endless support for that. And I definitely want to thank all the committee members because they give me a lot of great questions and force me to think deep about what did I find and what should I interpret and how should I present the results to the people who does not have the stats background. And I want to give special thanks for my family, both family in China and in the United States. Their support is phenomenal to me. And then last, I want to thank to the stats departments to give me these opportunities as to pursue my PhDs. And here are some memories that I have. This is taken in 2015. So literally 10 years ago. And I was way slimmer at that time, and I want to go back to that. And that is I think that's my mom's first time visits United States, so it's really great. And I want to introduce this beautiful graph that our cohort come up with. And I'm in the middle. Thank you to all my cohorts. And my husband is here for some reason. But they are the best type of cohort that I could ever wish for. And then I got this, I don't know, peak of my life that I have 3 talented white men hold me there. And then eventually we sign our document in the computer lab. And if you look in details, this is Nick, and this is me. And those both pictures is made by Emerson. And then we are trying to recreate that thing again. So that has been fun. And again, for people who don't know Emerson, he's really talented guy there. And then we signed our document there. And then we got married. And thank you for Pete for the service. And of course, not only the happiness things happen, this is miserable. If you look that close, so I was working from 9:30 at night and trying to submit my simulation to the cluster. And all these things is my simulations. And I haven't stopped until like 12, almost 1. That's how much time that I put for the simulation studies. So that's the pain. And again, my parents shows up again, and then we hang out again. Again, I become fatter. But we have an actual candidates there, my husband, and then I have my beautiful United States family now, and they're really talented and gorgeous and give me a lot of evidence. And that is the journey for my PhDs. And I am very grateful that you guys shows up, and I can take any questions that you have.